So we know that, 1 minute. Okay, we know that addition is one of the important concept in the computer organization. That means when we are using any arithmetical logical unit, that means the ALU, we must require the some technique for addition of the two numbers, two binary numbers. Actually, in the computer system, in the ALU, actually you know that we actually add two binary numbers because computer only understands the binary form. We can write the number in the high level language, but ultimately it will transfer to the binary form. And here the arithmetical and logical operation will actually computer will do the arithmetical logical operation on the binary numbers. Clear? Now simple addition, if I look to the simple addition, how to do the addition? Suppose 125 plus 145, we are adding these two numbers. You know, first we have to add these two digits, right hand side digits, that means called the least significant digit. So 5 plus 5, 0, carry. So we will have to add the carry with this, that means 4 plus 2 plus carry, that means the 7. Then we have to add this most significant digit, that is the 1 plus 1, 2. Okay. So this is the technique for addition of the two decimal numbers. The same technique will use for addition of the two binary numbers. Suppose this is the two binary numbers. The number is 0011. The decimal corresponding decimal is 3, and another is 0101. Okay. So if I add these two numbers, what will happen? First, we will add these two numbers 1 and 1 to rightmost binary number. That means 1 plus 1, that is the 0. 1 is carry. That carry will be added with these two numbers. That means 1 plus 0 plus carry. Again 0. Again there is a carry. So that carry 1 plus 1 plus 0. So again 0. So 1 is carry. So carry plus 0 plus 0. So 1. So 3 plus 5 we will get actually the 8. So 1000. This is the binary of the decimal value 8. We know this is the simple thing for adding of the two binary digits. For making the circuit in the computer organization, what we have to do? First, we have to add these two binary numbers. That means 1 plus 1. Whatever carry is generated, it will add it with the next binary number. That means 1 plus 0 and carry in. That is called the carry in, which is created from this. If I add this number, it will generate this sum and the carry out. That carry out would be the carry in for these two digits 1 and 0. It will add with the 1 plus 0 and the carry in, and it will get the sum. This is the sum, and again the carry out from here. This carry out will go here. It will be the carry in for these two numbers 0 and 1. It will add up with this carry in, so it will add up and it will go here. Again the carry which is came out here, it may be 1 or 0. It will add with these two numbers, and the final result will be this. So this is the technique. The same technique in the binary number is whatever technique we have used in this decimal number, the same technique is followed in the binary number. Okay, but here you have to design the adder for this. Okay, this we can do using the adder. Adder means the circuit which is required for the addition of the two binary numbers. Clear? So first we'll do for the 2-bit adder. Okay, 2-bit, 3-bit adder. That means called the full adder. What is full adder? Full adder means we have the 2 bits, only 2 bits, and carry in, C in. So suppose the 2 bits are A, B, and the carry in is this. The output will be carry out and the sum. Clear? Again, I repeat, we are adding 2 bits A and B with the carry in, C in. The result will be, we'll get one summation, sum result, and the carry out result. So as there are 3 bits here, A, B, and C, and obviously, what is the total combination we can generate? We can generate 2 to the power 3. That means the 8 combinations: 000, 001, 1010, 011, 100, 101, 110, 111. These are the combination. That means if the bits are 00, carry in is 0, sum will be 0, carry out will be 0. If both are 00 and carry in is 1, carry out will be 0, but sum will be 1. Similarly, if this is 0, this is 1, and carry in is 0, output carry out will be 0, but sum will be 1. Similarly, if A is 0, B is 1, and carry in is also 1. Here C out will be 0, but summation will be 0. In this way, this is the truth table of the full adder. Full adder means there are A, B, and carry in. We are getting the result carry out and S. Okay. Now, if this is the truth table we require for making a full adder, one addition of the two binary bits. Here we are adding only 2 bits. This carry out will be the carry in of the next 2 bits that I have shown in the previous slide. Okay. Now, see, we have to start from the basic. So what is the basic? Basic means we have to first find out what is the sum here. You can find out that here sum is A XOR B XOR C in. If I make XOR of the 3 bits A, B, and C in, we will get the summation. That means summation is actually the XOR of A bit, the 2 bits, and the carry. If I XOR, we'll get the sum. So this S is equal to A XOR B XOR C. This is the, if you put the values A and C, we will get the value of S here. If you put A, B, suppose A, B, and C all are 0, so 0 XOR 0 XOR 0, we'll get the 0 here. Similarly, suppose this one 1 1 1 1 means 1 1. That means that if you make the XOR, it will be 0, and you make the XOR with the 0, so output will be S will be 0. So you'll get the 0 here for this example. Okay. So this is the summation. Now the C out. Another is the C out. C out is the carry out. What will the carry out? Carry it out. If you go through the truth table, you can find out that carry out is nothing but the A and B, or B and C in, or C in and A. Okay. That means if you put the values of A, B, and C in here, you will get the C out here. If you check any row, if you check any row, you will find out that C out is nothing but the A and B, or B and C, or C and A. So we get two values, two output values, S and C out from the input values A, B, C, A. Now we have to design it using the gate. See, here in the gate, A and B, this is A and B, I have written in the capital. A and B is the two input, 2 bits, and C in is the carry. So here A, first what is happening? Here B XOR C. So B and C XOR, it will be XOR, and we are getting the output here B XOR C. This B XOR C will be XOR with the A. So A XOR B XOR C. So A XOR B XOR C. So it will be the S summation. Now here, what is the A and B plus B and C in plus C in plus S? So we require one AND gate and OR gate. So first we have to do the AND. So here this is one AND gate, 2 AND gate, and 3 AND gate. So 1, 2, 3. So one AND gate will do A, B. Another AND gate will do B, C, N. Another AND gate will do C, N into A. So this is the AND. After doing the AND operation, we have to add using the 3 input. This is called 3 input OR gate. We have done in the lab 3 inputs OR gate. So if I put the values in the 3 input OR gates, we'll get C out is equal to AB plus BCN plus CN plus A. So we are getting the C out here. Clear? So this is the simple circuit of full adder. The same block. This is the block diagram of the full adder. What is the block diagram? In the block diagram, you don't have to explicitly show the circuit. You only show the what is the input and output. So what is the input in the full adder? Full adder input is A and B input. Another is C in, A, B, and C in, and output we are getting, and one is sum S and another is C out. So this is the simple design of the full out. Now the thing is, when we are designing something in the computer architecture, computer organization, what we have to do, we have to find out what is the time it will take. And you know, then in digital circuit, actually time depends upon the gate delays. What is the gate you are using and what is the delay in the gate? Okay. So here, see what the total gate delays for making the full adder. Now see here, this all the things in this gate, in the AND gate, this XOR gate, and this OR gate, these AND gates, these XOR gates and these AND gates, they are doing the operation parallelly. That means at the same time, the input are given in this XOR gate and this AND gates. So time taken for this output here, this output here, this output here, this output here will be same. So what is the gate delay? Gate delay is one gate delay, because this is one gate, this is one gate, this is one gate, this is it. As they are doing operation in the parallel, so there will be one gate delay. Okay, so in the one gate delay, we will get the result here, 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 and here. Okay, next, this is another gate. This is for summation XOR gate, and this is the OR gate for Cout. So they are again doing operation in the parallel. So after getting the output here, 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 and here, what is the gate delay for the next output? One gate delay. So this is one gate and this is one gate. So what is the total number of gate delay? This output will get after one gate delay, and these two outputs will get for the another gate delay. So we will require two gate delays. For this reason, it is written here, two gate delays are required to get the output. That means if A, B, and C in is given, after two gate delays, we will get S and Cout. Remember that gate delays means gate requires some time. Suppose each gate requires 2 seconds. Suppose this is some example, or 2 nanoseconds or 2 seconds. So 2 gate delays means total time required. If it is 2 seconds, 4 second time will be required to get the output after giving the inputs. Okay, if it is 2 nanosecond, 4 nanosecond, because each gate takes 2 nanoseconds, so 2 into 2, 4 nanosecond will be required for get the output. One thing you must know that here, let's see here I have used 3 input OR gate. Okay, here if I use 3 input XOR gate, what should be the gate delay for S? In that case, gate delay for S will be 1 gate delay, because if there are 3 inputs, this one, and this one, come to a XOR gate which can take 3 inputs. So here directly we will get the value of S. So if we use 3 inputs XOR gate, the delay for getting the summation will be 1 gate delay. But obviously the delay for getting the Cout will be 2 gate delays. Clear? That means, again I repeat, if I use this type of circuit where there is 2 input XOR gate, the gate delay for getting the sum is 2. Gate delay for getting the carry is also 2. If I use 3 input XOR gate, the gate delay for getting the sum will be 1, because 3 inputs directly will go to the another input here, but Cout will only require the 2 gate delays. So 2 gate delays are required for the Cout if we use this circuit. Whatever circuit we use, 2 gate delays are required. Okay, now this is the full adder which can add 2 single bits with the C in and we'll get the output of Cout and S. Cout means the carry out and S is the sum. Clear? Now from this full adder, we will design the adder which we have shown in the previous slide. That means after adding, it will go to the Cout, will go there, it will be Cn for the next bit. So see here, this is our circuit for addition of the 2 bits number. See here we are adding A0, A1, A2, A3. This is a 4 bits number. It is clear from here. This is bit, and we are adding it with the B0, B1, B2, and B3. What is the result we are getting? We are getting sum as the S0, S1, S2, S3, and carry C0, C1, C2, C3, and C4 is the final carry. Clear? So what will happen? First, it will add A0 and B0 with the C0. So A0, B0, and with the C0. Remember that in this type of carry, C0 is connected with the ground. That means this value of the C0 should be 0, because it is not getting any value, so it should be 0. So I have not written here, it should be 0. It is connected with the ground. Clear? So A0, B0, and C0. This is the input of a full adder. You know what should be the output? Output is sum 0 and Cout. So Cout this C1. Now this C1, this is the carry in for this full adder. So now this full adder will get the value A1, B1, and this is the C in. Now this is the C1. It will get the S1. Okay. After getting S1, what will happen? After 2 gate delays, we will get the S1. So it will get C2 here. Now C2 will add up here, A2, B2, and C2. Output will be S2 and C3. C3 will go here. It will add with the A3 and B3, and output will be S3 and the final carry C4. This is actually the final carry for this summation. So what will happen? Here first it will add this. It will transfer or repel the carry or forward the carry to the next full adder. it will repel the carry to the next or forward the carry to the next full adder. This full adder again forward the carry to this full adder. So here carry is rippling for this position to this position from C0 to C4. So this type of adder is called a ripple carry adder. Here I have shown one 4-bit ripple carry adder. If you want to design 16-bit, you just cascade another 4 bits. If you want to design 8-bit full carry adder, you have to add again 4 bits full adder. Here one full adder, one full adder. That means another additional 4 full adders you have to add for designing of 8-bit ripple carry adder. If you want to design 16 bits ripple carry adder, you require 16 full adders. Okay, this is very easy to understand because we actually do the summation in the decimal in this way. This is very easy to understand and this is very easy to design also. Clear? Because if I design one full adder, if I connect it cascadingly or connect one after another, we will design one big addition adder operation. Okay, but there is a problem here. What is the problem in the ripple carry adder? This is very important. Problem is the time required by ripple carry adder is very high. Clear? Why? What I have told that 2 gate delays are required for making the C1. So after C0, if you give the input here, after 2 gate delay, it will go here. After 2 gate delay, C2 will go here. After 2 gate delay, C3 will go here. That means 1, 2, 3, 4. There are 4 full adders. 4 into 2. That means total 8 gate delays are required to get the output C4. Okay. Now, what is the time for getting the summation? Full summation. After 2 gate delay, we will get this summation. Another 2 gate delay, this summation, this summation, this summation. One last summation, it may be, there may be possibility that 1 gate delay less is required, 7 gate delays are required. Why? Because if you use the 3 input XOR gate, I have told you, there will be 1 gate delay less you can use. That means you will get the output of the summation, whole output after 7 gate delays, not a gate 8 delays. If you use the 3 input XOR gate, but if you use the 2 input XOR gate that I have told you, obviously you require the 8 gate delays. 2, 2, 2 plus 2, 4 into 2 is equal to 8. Clear? Here I have shown here that gate delays getting carry C4 in full bit for adder is 2 into 4. That means the 8. Clear? So gate delays for S3 is 2 into 4 minus 1 because 1 gate delay is required if I suppose we are using the 3 input XOR gate. So if there are, this is a 4-bit adder. Okay, 4 bits adder, so you will require 8 gate delays. Suppose this is a n-bit adder. What is the gate delays will be required? Maximum gate delays will be required 2 into n. 2 into n. Suppose there are 16 bits. So what is the time required? 16 into 2, that means 32 gate delays. If each gate requires 2 seconds, that means it will require 32 into 2. That means the 64 seconds for completion of this sum, and it is huge time. 64 seconds with respect to the computer or the processor is a huge time. That means your computer will be very slow. If I use 64 means more than 1 minute. It will be very inefficient if we use this type of circuit for summation of a large numbers. Clear? So this is the limitation of the ripple carry adder. Okay, that means when you are asked that what is the advantage of ripple carry adder, you will tell that advantage is that it is very easy to design and it is very simple to understand. Now, what is the disadvantage? Disadvantage means it is very time consuming. It is not efficient design for summation of the 2 numbers because it will take the more time and it will make your computer very slow. The efficiency of the machine will be decreased even you are using a high-speed machine. Okay. So what is the alternate of ripple carry adder? Alternate of ripple carry adder is a carry look ahead adder. Okay, this is simply the alternate of ripple carry adder to solve the problem of time consumption by the ripple carry adder. So this topic is the carry look ahead adder. What is the meaning of that and how it is realized? See here. We know the Cout formula is AB plus B into Cn plus Cn into A. We know that. Okay. That means we can write here as a see I plus 1. I plus 1 means the next carry out. I plus 1 is equal to AB plus B in B and CI, or CI into A. We are writing the same thing we have written here. This we can write it in this way: AB, AB is same, plus we are taking common as the CI. So B XOR A into CI. CI you are taking common, so B XOR A is equal to CI. Okay. Now we will ask whether this is equal to this. Yes, this expression is equal to this expression. Here I have simplified the expression. If you put here and if you simplify it, we'll get this expression AB plus ACI plus BCI. That means that this expression. Here I have written the. You can go through this, then you will understand. So we are writing this expression as a this, and here we are writing AB is equal to GI and B XOR A as equal to PI. What is the meaning of GI and PI? We are writing this AB as a GI and B XOR A as a PI. So GI is carry generate and PI is called the carry propagate. Again, see here A into B is equal to GI. This GI is called carry generate, and PI for P, that is called the carry propagate. Carry propagate PI is equal to B XOR A. Clear? We have written, that means nothing. We have written the same expression in the another way in the form of the G and P. Clear? So now what happens? So that means we know now CI plus 1 is equal to GI plus PI into CI. This is our simplified expression. Again, I repeat, CI plus 1 is equal to GI plus PI into CI. This is our simplified expression. Now see what happens from this expression. See here. So we can write C1 is equal to D0 into P0 into C0, because I have already told CI plus 1 is equal to GI into PI into CI. You put in place of the I as a 0. If I put 0, it will be C1 and it will be Z0 plus P0 into C0. So here I have written here C1 is equal to Z0 plus P0 into C0. Clear? Now we know the value of C1. What is C2? C2 is equal to G1 plus P1 into C1. C2 is equal to G1 plus P1 into C1. Now we know the value of C1. So if I put the C1 and simplify it, it will be G1 plus P1 G0 plus P1 P0 C0. Clear? This is the simplified expression of the C2. Then comes the C3. C3 is again C2 G2 plus P2 into C2. So we know the value of C2 from here. We put here, we simplify, we will get the value G2 plus P2 into G1 plus P2 P1 into Z0 plus P2 P1 P0 C0. This is all of the AND. I am telling about this is into, but this is AND operation. Okay. Again, from C4 we are getting this. Now see here one thing. All the forward expression, one thing will be clear, that at the time, what is the value of Z0 and P0? Z0 means A0 B0 and P0 means A1 XOR B1. We know this. And C0 we know that is 0. That means what happens? What is the problem in the ripple carry adder? When we are giving the C0, it will first generate C1, C2, C3, C1. But from the expression, it will be clear from all the full expression that at the time it will get A0, B0, A0, A1, A2, A3, and B0, B1, B2, B3, and C0. Instantly, it will generate the C1, C2, C3, and C4. Because this expression, the meaning of this is, because we know at the same time what is the value of P0, P1, P2, P3, and Z0, Z1, Z2, Z3. When just we are giving the input, we are generating the carries at the same time. Okay. So what will happen? The circuit does not have to propagate the output carry from one full adder to another full adder. It will generate instantly all the carries given here when you get the inputs. What are the inputs? Inputs are nothing but A0, A1, A2, A3, B0, B1, B2, B3, and C0. That means from this C0, this all the carries are nothing but the functions of A, B, and C0. Clear? That means the result suggests that the 4 carries can directly generate from the C0. It don't have to propagate. It don't have to repel. Clear? So this is the advantage of using the carry look ahead adder. It will be clear if I go to the circuit. Now see here the circuit of carry look ahead adder. First, it will give a A0, B0, A1, B1, A2, B2, A3, B3, C3. These all are the inputs, these and this. These are the inputs. At the same time, you will give the input. When you are giving the input, what will happen? You know that G0 means A0 and P0. So AND gate, and P0 means A0 XOR P0. So this is a XOR gate. So all the operation we will do it in the parallel. Which operation? For getting the output of P0, G0, P1, G1, P2, G2, P3, B3 within one gate delay. This is only one gate delay. Why? Because they are doing operation in the parallel. So one gate delay, after just one gate delay, we will get the output as G3, P3, Z2, P2, Z1, P1, Z0. After one gate delay, then comes this circuit. What will this circuit do? This circuit will do nothing but this AND operation and OR operation. Okay, first you will do the AND operation. AND operation means P0 into Z0, P1 and P2 and C3. This AND operation and OR operation. What is the gate delay required for this? 2 gate delay, because for AND operation, it will do in one gate delay parallelly, and then all the OR operation it can do the parallel. So 2 gate delays are required for AND operation and OR operation. Here 2 gate delays are required. So 1 gate delay, 2 gate delay. Last one is we are adding this P0 XOR C0. Okay, P0 XOR C0. So here last one is P0 XOR C0. This is the XOR operation for summation. So this summation operation will do here, and here we will get the values of summation S0, S1, S2, and S3. So what is the gate delay? 1 gate delay. Here 2 gate delay, 2 plus 1, 3 gate delay, and last one is the 4 gate delay. 1. That means the 4 gate delays are required for completion of the operation for the 4 bits number. And what is the previous one? 8 gate delay. That means the double time required is the double. Clear? Similarly, if I use the 8 bits, the gate delay will be 4. If we require for addition of the 16 bits number, gate delay again will be 4. Okay, so this is the 1 gate delay for all GIs and PIs, 2 gate delays for all CIs are available, and 1 gate delay for the sum. So total 4 delays to get the output. Okay, so this is the advantage of using the carry look ahead adder. Now, what is the problem with the carry look ahead adder? Problem is this circuit. This circuit is little bit complex, as that means there are some costs required. When your time is slow, that means some cost is required for this. Here cost is in the term of the circuit complexity. Yes, circuit is little bit complex, not like the previous one. Previous one was very easy. So this is the advantage and disadvantage of using the 4-bit carry look ahead header. CLA means carry look ahead header. Okay, so this is for today.